Hey everyone, it's Dr. GB, and today I'm going to go over resonance structures for two of our in-class problems. So the first one for NNO and the second one for CO32-. Alrighty, so let's go ahead and let's start with NNO. Alrighty, so the first thing we do whenever we do a resonance structure is we add our number of electrons together. So N is going to have 5 valence electrons, this N is going to have 5 valence electrons, and O is going to have 6. That's going to give us a total of 16 electrons. All right, so I'm going to go in, and so I put in the notes that the central atom underlined is going to be an N, all right? So we're going to have an N with an N on one side and O on the other side. We're going to draw a single bond between each, alrighty, and that's going to be our skeleton structure. That's 4 electrons. We'll subtract 4, we have 12 electrons to deal with. So when we deal with the resonance structure, we are going to, after we've made our skeleton structure, we take the remaining electrons and we put them to complete the octets of the outside atoms. Alrighty, so we are going to go, so first I will complete the octet of the oxygen, so 1, 2, 3, 4, 5, 6, and then we complete nitrogen, 7, 8, 9, 10, 11, 12. Alright, so we've used up all 12 electrons and we have 0. Now if we take a look at this resonance structure, it may look like it's okay because nitrogen and oxygen both have their octets completed. However, we have a big problem here. That's that nitrogen only has 4 electrons and we wanted to have access to 8. So the question then becomes, how do we go and give nitrogen an octet while also giving oxygen and nitrogen an octet too, but not changing the total amount of electrons? So we have a few different options that we can do here. The first is we can have nitrogen and oxygen each contribute a double bond. So what that would do is that would give us this structure here. Alrighty. Another option that we can do is, because ultimately we want all of our atoms to have access to 8 electrons, and the way that we can do that is for nitrogen to make 4 bonds. We can't have that central nitrogen have a lone pair because to keep that total number of 16 electrons, that nitrogen is going to be having to make 4 bonds. So the other option that we can do is we can have nitrogen contribute 2 more bonds and then have oxygen stay with 1 bond. All right, so we have nitrogen. That's an option. And then finally, the last option we'll see is nitrogen sticking with 1 bond, and then oxygen contributing 2 lone pairs to have a single bond between the 2 nitrogens and then a triple bond between the oxygen. Alrighty. So we have 3 potential resonance structure options here. So the question then becomes, how do we know? First of all, we need to check the formal charges to determine if they're valid structures, but also we want to figure out which is the best and which one is the worst, if there's any. Alrighty, so let's go ahead. So I'm going to go ahead and I'm going to put a 1 here so we know which N is which. So we're going to go ahead and we're going to determine the formal charges for all of them. N1, N2, and O. Alrighty, so in each structure. So in N1, nitrogen has 5 valence electrons. It starts out with 5 valence electrons. It has 4 electrons and lone pairs there. And then it has 1/2 of 4 electrons and bonds. That gives us 5 minus 4 minus 2 is minus 1. All right, over here in this structure, nitrogen has 5 valence electrons. We subtract 2 in lone pairs minus 1/2 times 6 in double bond in bonds, and that gives us a formal charge of 0. Again, nitrogen has 5 valence electrons. That likes to make 3 bonds and have a lone pair. So in the middle structure, that nitrogen has a formal charge of 0 because it's happy. It's making the number of bonds and lone pairs that it wants. Then finally, on the right-hand side, we have 5 minus 6 electrons in lone pairs minus 1/2 times 2 electrons in bonds, and that gives us a charge of minus 2. Alrighty, let's go to the second N. Alrighty, so in the first structure, all of our nitrogens, we always have 5 valence electrons to start. Minus 1/2 times 8 electrons of bonds gives us plus 1. And the second structure, that N2, is 5 minus 1/2 times 8 electrons. It's just instead of being 2 and 2, it's 3 and 1 equals plus 1. And then finally, same dealio on the third one, 5 minus 1/2 times 8, except we're 1 and 3 instead of 3 and 1 or 2 and 2. And that gives us plus 1. And finally, let's take a look at the oxygen. So oxygen has 6 valence electrons because it's group 16. Alrighty, so we have 6 minus, in the red structure, 1, 2, 3, 4. So minus 4 lone pair electrons minus 1/2 times 2, 4 electrons and bonds gives us a charge of 0. Alrighty, looking at the 0 in the oxygen in the blue structure, minus 2, 4, 6 electrons in lone pairs minus 1/2 times 2 electrons in bonds gives us a charge of minus 1. And then finally, for our structure in green, we have 6 minus 2 electrons in lone pairs minus 2, 4, 6, 1/2 times 6 electrons in bonds, and that gives us a charge of plus 1. Alrighty, so let's take a look at these structures. The first way to figure out if they're valid is we all know they have the right amount of valence electrons, so we're good to go overall. But then we want to make sure the charges, the formal charges, add up to the charge of the molecule. So NNO, I don't have a plus or a minus there, so it was a neutral molecule. So we want to make sure our formal charges add up to 0. All right, so you got minus 1 plus 1 and 0 gives us a charge of 0. So this is a valid structure. 0 plus 1 minus 1 adds up to 0. Then finally, over here in green, we have minus 2 plus 1 and plus 1. Okay, minus 2 plus 1 is minus 1 plus 1 is 0. We check out. Okay, so then the question becomes, how do we rank the structures from best to worst? Alrighty, so first things first, if we identify the worst structure, remember, the best resonance structure is going to have the smallest number of non-zero charges, and they're going to be the smallest in magnitude. So right away, number 3 is going to be green, because every atom has a charge, and one of those has a magnitude of 2. So that's going to be our worst, because we have every atom has a non-zero formal charge, and one of them has a big one. Then that brings us over to the 2 structures on the right. It may look like the structure on the left. It may look like the red and blue structures on the left are tied, because in both cases we have a minus 1 and a plus 1. But on the left, we have a minus 1 plus 1 and 0 versus a 0 plus 1 minus 1. Now, in both these cases, the plus is on the center nitrogen, so that's not going to be our deal breaker. The question then becomes the placement of the oxygen, or the placement of the negative 1. Remember, we want the negative charge to be on the least electronegative atom, all right? So which atom is, so we have one where we have a negative 1 on nitrogen, and we have one where we have a negative 1 on oxygen. Which of these is less electronegative? So if you go into your skeleton notes, you can look at your Pauling electronegativity table. Nitrogen has a electronegativity of 3, oxygen is 3.5. So this structure over here is going to be number 2, because N is less electronegative than O. And then our best structure is going to be the center one, because it has the negative on the oxygen. Alrighty, so the best structure is the one that minimizes the number of formal charges and puts the negative 1 on the most electronegative oxygen. The next one is minimize the charges, but it puts the negative 1 on nitrogen, which is slightly less electronegative. And then our worst one is our resonance structure, where we have multiple non-zero formal charge on every atom, and one of them is minus 2, so it's big in magnitude. Alrighty, so let's go ahead and let's do another resonance structure. So we're going to do CO3 2 minus. Alrighty, so CO3 2 minus. So carbon has 4 valence electrons. Alrighty, oxygen has 6. We have 3 times 6, and then we add 2 valence electrons. So 18 plus 2 is 20, plus 4 gives us 24. Alrighty, so let's go ahead and let's make our skeleton structure. All right, so we have carbon. So you may be wondering, Dr. GB, what do I do? So our hint that we're going to structure this in a certain way is carbon is less electronegative than oxygen, so we'll put it in the center. Then we have 1 carbon, we have 3 oxygens. So that's like our hint that we're going to put carbon on the inside and oxygen on the outside. Alrighty, so what we're going to do is we'll draw carbon. We'll draw the 3 oxygens around, alrighty, and then we will draw a single bond between each of the carbons and the oxygens, alright? So that's 2, 4, 6 minus 6 electrons, and that gives us 18 electrons left over. So what do? We go ahead and we complete the octets of our outer electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Alrighty, that gives us 0. So we've used up all of our electrons And all of our oxygens have complete octets. But is this molecule happy? No, it's not. We have a big problem here, and that carbon is missing. It doesn't have a full octet. It has 6 electrons. It needs 2 more. So what do we do when we have the right number of valence electrons, but our central atom is missing its octet? We go and we make a double bond with an outer electron. But then the question becomes, which oxygen? This oxygen could go and donate an electron to make a double bond, or we could have this oxygen, or we could have this oxygen. Alrighty, so let's take a look. So we have this option. That's a minus, by the way. It's a minus charge. We have this option. Whoops. Okay. C. Whoop, sorry, y'all. Merp. Okay, there we go. Is it Friday yet? No? Okay, we'll keep going. Gotta put that one there. Alright, so we have these 3 options, alrighty? And so if we go in and we were to determine the carbon in this case, all of the carbons start off with 4 valence electrons, and they have 8 electrons in bonds, no lone pairs, so they have a formal charge of 0. So all those carbons are going to have a formal charge of 0. The oxygens that have a double bond, alrighty, they start off with 6 valence electrons, they have 4 in lone pairs, minus 1/2 times 2, or times, 4 in bonds, that gives us 6 minus 4 minus 2 gives us 0. Alrighty, so these electro-oxygens that have the double bonds are going to be a formal charge of 0. And then finally, we are going to go through and we check out our oxygen that has the single bond with 6 lone pair electrons. Alrighty, so we start off with 6 lone pair electrons. We have 2, 4, 6 minus 6 electrons in lone pairs minus 1/2 times 2. And that gives us 6 minus 1 gives us minus 1. All right, so all of those oxygens that have a single bond in 6 lone pairs have a formal charge of minus 1. Now, all of these structures are valid because 0 plus 2, 0 plus 0 plus minus 1 gives us a charge of minus 2, which matches our overall charge. The question then becomes, which of these is the best structure? All of these structures have a formal charge of 0 on the carbon, and they have 2 negative ones, and they're each on a different oxygen. So none of these structures are better than the other. They're all equivalent. And in fact, if you were to go and you were to make bond angle measurements of all of those CO bonds, what you would see is that actually each of those bonds is 1.33 bonds, and you would see okay, so 2/3, 2/3, 2, 4, 6, this would be, each of those would be about 1 1/3 bond lengths, and each of that area would have a charge of like minus 2/3, alrighty? So all of those resonance structures, so whereas with NNO, the center structure would be the biggest contributor, followed by the left, followed by the right. For CO3 2 minus, all of these structures would contribute equally because they're all the same. They're just rotated 120 degrees, and the average would be evenly weighted between all 3. Alrighty, well, I hope that this video has been helpful for you. If you have any questions, please don't hesitate to come to student hours. Y'all have a great day.